All right, AP students, welcome to your acid-base pre-lecture, Introduction to Acid-Base. This is another special type of reaction category. We previously talked about in another lecture about double displacement precipitation reactions. Acid-base are another type of double displacement, but they're actually an entire unit to itself in the AP curriculum. And we're just going to start introducing ourselves to the concepts this unit. And then in unit 8, we're going to delve far more deep. So to begin, how do we define an acid or a base? While there are several definitions that exist, we will be using the Bronsted-Lowry definition, which says that an acid donates is a compound that is able to donate an H plus proton. Okay. Sometimes when we talk about the H plus proton, because we often do these acid-base reactions in an aqueous water environment. We can also say that it's an H3O plus hydronium ion, which is just a more realistic way of us expressing how that H plus proton is carried in the water as an H attached to a H2O, giving us a positive charge water molecule, essentially. So they're one and the same, all right? And then as a base, we say, according to the Bronsted-Lowry definition, that they are compounds or species that can accept an H plus proton. It's not always the case, but oftentimes you will see a strong base, often being able to carry its own recognizable ion that is able to accept that H proton. And we could say that it is also a compound that possesses an OH hydroxide. Okay. So an OH hydroxide ion is an anion that would readily accept that H plus proton. So this is kind of a second way that falls under the general category of the base definition of ability to accept an H plus proton. It's an easy way to identify when we're working with really strong bases that are really likely to accept an H plus proton. Okay, so neutralization occurs when we have an acid that H plus donator, okay, react with a base, that H plus acceptor with a base, okay, to produce a salt, semi-ionic compound, and water. Essentially, right? All right, removing the ability of a compound that now carries a distinct H plus and a distinct OH minus, okay? So neutralization is really just the idea that you no longer have this distinctly acid and distinctly base that exist in solution. Now, I want to make a quick note that this understanding of neutralization when it comes to producing a salt and water is particularly true for strong acid and strong base reactions. We do have categories of weak acid and weak base that will kind of adjust what we see as a product. All right. So I do want to make that as a general consensus that neutralization is basically anytime an acid or base react together. And then as far as producing a salt and water, that's particularly identifying of a strong acid, strong base neutralization. We say that when we understand neutralization quantitatively, we would say that this occurs when the moles of your acid stoichiometrically equal the moles of base. So if my balanced chemical equation says that the reaction occurs in a 2-to-1 ratio of acid to base, then when I am at a point in my solution, my mixture of acid and base, where I have 2 moles of acid for every 1 mole of base, I am neutralized. All right, so if you look over here, we have an example of acid-base neutralization. And we actually have an example of a weak acid-base neutralization, but the idea is that we have, here we have water acting as the acid and ammonia, NH3, acting as the base. Water is going to be a proton donor here, and the NH3 is going to be the proton acceptor. All right. And so when we see an acid base neutralization, and I will make a quick note that this is particularly a weak example. And I not weak as in bad, weak acid, weak base example. Okay, weak acid, weak base example. What we see is that we get this, what we call a conjugate pair form. We see that our acid becomes our base as a product with that proton transfer, and our original base becomes our acid. All right, because the root of that chemical compound is just gaining or losing a proton. So for a conjugate pair, we say the conjugate acid, all right, is the base with an additional H plus. It was the original base. I'll say the OG base, right? Is that maybe too slang? We'll say original. It was the original base with an addition of an H plus. So here our conjugate acid is NH4 plus, ammonium, polyatomic, okay? And then we would say that our conjugate base was our original acid minus an H plus, minus a proton. So we say for us, our conjugate base, oh, not that color, sorry. Conjugate base is OH, and that's definitely supposed to be a minus. I don't know why that looks like a plus, okay? An OH minus, all right? And a hydronium ion. Okay, so for a couple practice problems, can you quickly identify what would be the conjugate acid of the original HSO4 minus ion? What was the conjugate base of the original HNO3 molecule? And go ahead and just do that for one moment. Okay, hopefully you did this, and all you need to understand is if I'm looking for the conjugate acid of HSO4 minus, what I'm saying is that this is going to be an addition, the molecule with now an additional H plus. So I would say H2SO4 hydrosulfuric acid. And if I'm talking about the conjugate base of a compound, that means I'm going to remove an H plus. What would that compound be without an H? And it would become NO3 nitrate minus, okay? 1 minus charge. So these are the types of dream FRQs that you hope to get. And let me quickly go into how we categorize what a strong versus a weak acid or base is. So a strong acid or base, all right, is an acid or base that completely, what we say, ionize in solution. That means every H plus is lost / gained, or maybe the best way to say is transferred. Every H plus available is transferred, okay, to the respective acid or base. All right, that's a strong acid or base. For a strong acid, every single H, okay, carrying molecule of that acid will release it, okay, to a base. For a base, for a strong base, every single base molecule will gain an H plus, all right? Complete ionization. All right. FYI, we often hear that bases are called alkaline. That's another term for a base. All right. So you'll often hear when you talk about alkaline water, it's a basic water. It is an H plus receiving water. All right. It's got a ton of compounds that can now carry an H plus and are ready to accept an H plus. But what about weak acid or bases? Well, weak acid or bases are what we call partially ionizing in solution. So that means not every, or maybe I should put the word some, only some H pluses are transferred. So with a weak acid or base, not every single molecule is going to give up that H or accept that H. Some of them are going to be like, no, I don't really need it. Okay. It's not as favorable to give it up or to receive it. It's possible, but it's not as favorable. So here's some weak acid and strong bases and weak bases and strong acids to honestly just memorize and be familiar with. I wouldn't pour a ton of energy into memorizing all of these. I would simply have a good idea of some common ones and then let the problems teach you. Just when you do practice problems, because everyone should be doing practice problems, you just take mental note. Oh, that was a compound used in an example of a weak, or that was a compound used in an example of a strong. All right. So there's another way that we can quantify or indicate whether we're working with a strong acid or strong base. And that is with a pH scale. A pH scale is a measure of acidity or basicity. All right. And it goes from 0 to 14. All right. 0 to 14. And it does pair up with a color. You'll often see what we use is a solution known as a universal indicator. That is a liquid solution that will drop in to a mixture of an acid or a base, and we will note the color on the spectrum to indicate what pH value, where we fall on the scale of acidic and basic or alkali. Okay. There are several methods, other instruments or pH measuring instruments we could use. And instruments is actually kind of a loose term. So what we could do is regarding the type of instruments or tools that we can use for measuring pH is we can use what we call pH colored paper or pH paper strips or as I mentioned before, indicator solution or indicator solution, right? Such as universal indicator. These are not as precise, but they're really useful. They give us a good idea, right? And then, of course, we would use other methods to create more exact, precise quantification, right? That would tie into this idea of moles of acid stoichiometrically equal to moles of base. What you should be thinking about is, oh, we're definitely going to start getting into stoichiometry at some point with acid and base, all right? But for now, we'll keep it at the simple tools that just kind of give us some colorful ideas. We also have some useful and slightly more precise instrument regarding pH measurement, known as a pH meter or electrode. And these are far more precise. They're digital, and they'll give us a more precise value regarding where it falls on the pH scale. But if you truly want exact precision regarding acidity and basicity present in solution, we're going to eventually have to do some math. But these are really useful nonetheless, and we'll use some of these in our titration labs coming up. So generally speaking, what you should notice is that acids have a pH between 0 and less than 7, and bases have a pH greater than 7 and equal to or less than 14. It's in that range. What does pH really mean, by the way? What does this term even mean? Well, pH is technically mentioning or measuring the potential of H plus ions. And notice I am bracketing my H plus because it's actually measuring the potential of H plus concentration, the presence of H plus acidic ions. We have an equivalent from a basic perspective where we could also measure the basicity or acidity from the point of view of the potential of OH minus ions, coming from a basic perspective. Either way, the calculations of what this actually translates to in a math process is that pH is equal to the negative log of the concentration of your H plus, or POH is equal to the negative log of the concentration of your OH minus, hydronium ion, in a strong base. And it's really helpful to know that when you put pH plus POH together, we get a standard relationship that says that pH plus POH values will equal 14. Notice that kind of mimics our pH scale, that the max we can have is 14. So however basic, all right, however basic a solution is, its acidic nature will quantify to the sum total of 14. However acidic a solution is, its basic nature will add up or quantify to the sum scale of 14 on the pH scale. So what you're seeing is, if I measure in pH perspective and I measure a 2 on the pH scale, then I would expect that my POH value would measure the remaining, the opposite, right? That I'd be way less basic, okay? So that's just kind of a conceptual representation and a manipulation of the pH scale, and also an indicator about why it's so useful for us, because we can kind of flip and flop between them, but we know that together they should accumulate in the complete potential of acidity and basicity for a given solution. So go ahead and try these practice problems regarding calculating pH or going between POH and pH perspective for a given solution. And then when you're ready, go ahead and resume me. All right, so hopefully you tried these problems. You should have gotten for the first one that the pH of strong acid with a 0.75 molarity concentration would be equal to negative log of 0.75. And that would give us a value of 0.12. Okay, how about for the next problem? Calculate the pH of strong base with 0.75 molarity. You should have noticed that you had to use pH plus POH equals 14. So when you did is you rearranged it and you said, well, the pH is going to equal 14 minus the negative log of our base, because we were given the concentration from the base perspective of 0.75. Okay. And you should have gotten a value of pH is equal to 13 points. Let's see, 8. All right. So super, super basic, which makes sense given that we have a pretty strong base with a high concentration. So our acidic nature would register more basic, right? And then of course, we do a similar thing, but now going from the pH to POH scale, we would have to use the equation that pH plus POH equals 14. And we rearrange the relationship. So we would solve for POH is equal to 14 minus the negative log of 6. Oh, I didn't even have to do math. What am I doing? It's so much easier. I am given the pH minus 6.3, and I get a value of 7.7 on the POH scale. So I'm a 6.3 pH or acidic behavior, and I know that its total behavior must be sum up to 14. So I know that from a base perspective, I am a 7.7 on the POH scale. Okay. And I really hope I did my mental math right. Okay. So water is a little bit unique. Water is what we call amphiprotic. So here, water, what we say, is able to be an acid or a base, depending on the context it's in. And as a result, we say that water is in equilibrium. And that means water, by the way, is an example of a weak acid and a weak base. And when we talk about equilibrium will be more in unit 7. This is kind of a unit 7 concept, but the idea is connected to the fact that with a weak acid or a weak base, we only partially ionize. So that means only some of the reaction is going through, not all of it. It's not a single arrow completion. It's a, well, we get some and then we don't, and then we get some more and then we don't. All right. So equilibrium is far more a unit 7 concept, but we're going to get introduced to it with the unique nature of water. Okay. We say that when water is in a solution of its own, like it's just straight a water sample, a water substance, like nothing else in it, we say that the pH of water is always 7. Here's why. It's always what we call the defining neutral solution, because it's always donating and, or what we call protonating, donating a proton, and deprotonating, accepting or removing a proton with itself in a 1-to-1 ratio, therefore always undoing its production of an acid, a conjugate acid, and a conjugate base. It's always 1-to-1 neutralizing its relative acidic molecule and its relative basic molecule, and therefore becoming a self-neutralizing 1-to-1 molar equivalent acid-base reaction between its own molecules. So I've mentioned this before, but this is also partly one of the reasons why water plays such an important role as the solvent for acid-base reactions, because it almost acts like a neutral inert species, all right? Unless specified otherwise. There are times when water is the base or is the primary acid. But when you have an acid or a base that's not a water present in solution, we consider then water just kind of like a neutral character that almost acts like a spectator and simply a carrier of the ion. All right. So that's why we again mentioned that H plus is often referred to as a hydronium ion, because we just say water carries it when it's acting as a neutral solvent, a neutral player in an acid-base reaction. Okay. So quickly identify in these practice problems whether water is acting as an acid or base. And pause me when you're ready, and then restart me. Okay, so hopefully you took a moment to look at this, and here what we see is water. The conjugate pair between water is it starts off with one less proton and it gains a proton. So we would say here that water is originally acting as a base and creating a conjugate acid. As far as the second one goes, though, we see water here with its conjugate pair. It starts with an extra H and it ends with one less H. So we would say that in this situation, water is acting as the relative weak acid. All right, so that's our pre-lecture. Tomorrow we'll pick up with titrations and start quantifying with stoichiometry the presence of acid and base, or H plus and OH minus ion. So really good work, you guys. See you soon.